So we had some good feedback from the video on WanaCrypt, but some questions about basically what it is that it does from an encryption point of view. And that actually is quite an interesting topic because what it does is similar, obviously slightly different, but similar to what most of the other ransomware does as well. So I thought we'd cover pretty much the basics of what it is that ransomware does beyond just it has a private key and it encrypts your data, which is obviously the assumption. We'll perhaps start with a look at a really rubbish one that I'm making up as I go along, and we'll kind of build it up into a system that kind of makes sense, and you'll see hopefully how it uses both symmetric and asymmetric or public key cryptography combined to try and produce an effective exploit. Okay, so let's imagine that I wanted to write a piece of ransomware, which I don't, I should add. I don't think people should be writing ransomware, but knowing a bit about how it works is quite a good way of understanding a bit about how cryptography works. There's really two major types of cryptography that we see a lot of, right? Symmetric encryption and asymmetric encryption. Right? We'll put hash functions aside for one day. So symmetric encryption quite simply has one key for encryption and the same key for decryption. Right? So AES is a good example of a symmetric block cipher that people use a lot of at the moment. Asymmetric encryption or public key cryptography is where we have a separate key for encryption and another key for decryption. Right? And that has numerous benefits in some circumstances and drawbacks in other circumstances. So what WanaCrypt does is combine both of these things to try and get a solution that first of all will run offline. So if they're not connected to their command and control servers, they can still encrypt your disk and theoretically decrypt it later, although the jury's out on whether they actually will bother. So let's imagine that we're writing some ransomware. Right? The first thing we could do is we could choose a symmetric encryption cipher like AES, right? And we could say, right, we're going to use AES, and to do that we need a symmetric key. So I could, as a developer, and I'm programming this up, I could write a piece of code that searches through all the files on someone's hard disk, and for files of a certain type, I could replace that file with a copy of that file that's been passed through this cipher. So I need to come up with a key. So I generate a key. So let's call it KS, right, for a symmetric key. The difficulty here is if I'm going to use this key to encrypt people's data, it needs to have access to it. So either this needs to be sent to the malware as it's running, right, in which case there's going to be a compromise there. The key's been sent over the network. Hopefully researchers could find it on the network and then use it to decrypt someone's files without having to pay any money. Alternatively, as a very naive approach, you could just bury it inside the code, right? People do this a lot, right? There are actual ransomwares that have done this. It's not the best approach. So you basically put this string, KS, somewhere in the code, and then the ransomware is able to encrypt it, and when it wants to, decrypt the files, right? Now, obviously, that's not a good solution, because anyone disassembling this code, right, and researchers do this within minutes of code being released, will immediately find this string and then tell everyone, oh look, the key's in the file, let's just decrypt it this way. And they'll write another tool that uses the same function and the same key. Right? So that's not a good solution. To improve on this slightly, we can bring asymmetric encryption in. Right? So this is our first attempt. I'm working my way towards something competent, right? So don't judge me yet. So in asymmetric encryption, we have two keys, right? We have a public key and a key private. Okay. Now, as long as the private key is kept secret, then in some ways we can encrypt everyone's files with the public key, and when they pay the ransom, give them the private key. That's kind of a general idea. So early ransomware worked this way. So when the ransomware started, it would generate a public and private key pair. It would send the private key off to a server somewhere to hold it for ransom, and then it would encrypt everything with the public key. This usually uses RSA. There are other options. And we won't talk about the mathematics of RSA, except to say that it's very, very difficult to calculate this private key given only this one. So if you're not watching this when it gets installed, this private key is gone, and all you can see is a public key, right? And then you're in a bit of trouble. Now, there's a few downsides to this. The first is that asymmetric encryption is quite slow, right? The mathematics involved in RSA is, it's not too bad on a computer, but we do it generally for smaller messages. If you were trying to encrypt a lot of someone's files with this, it would take quite a long time. And also, you have to have a connection to your command and control server. If your malware is running, and let's say they're temporarily not on a Wi-Fi or something like this, then what happens is it tries to upload this private key and it can't. So one of two things happens then. Either it has to stop, or it just encrypts everything with the public key and we lose the private key. Or the private key has to be temporarily stored on the disk, which isn't going to work well for holding it for ransom, right? None of these solutions are very, very good. So that isn't a very good solution either, right? It's a bit slow, and there's an issue of trying to upload this to a command and control server, and how we're going to do that. Right? So what modern ransomware does, and this is not exclusive to ransomware, lots of encryption schemes work this way, is a hybrid encryption scheme, where the majority of the encryption, so the actual encryption of your files, will be done with AES or some symmetric cipher, and that key will be protected by public key cryptography. So you're holding one of these private keys for ransom, and when you get it back, you can then unencrypt KS and unencrypt your files. That's the idea. So this is what WanaCrypt does. So WanaCrypt will install itself in a directory, and it starts undertaking lots of different tasks. One of the tasks it does is start up threads for trying to spread itself using the Eternal Blue exploit. But the majority of the work in terms of encryption is separate to that. And what it will do, from inside its own executable, it will extract a zip file, which is also encrypted. It will decrypt this using a password, and then it will extract those files. Now, they hold things like hard-coded Bitcoin addresses that we know about, that you're supposed to be paying this ransom, hard-coded public keys of the server, which I'll talk about in a moment, the addresses of the Tor addresses of the server for the Tor hidden services. It extracts all of these things, and then it gets to work encrypting your files. So the first thing it does is it generates an RSA key pair. If I start a new page, then we won't be confused with my terminology, but essentially I'm making up as we go along. So,
did you solve that Rubik's Cube since we...
I changed a couple of pieces around. I haven't solved the ghost cube yet. I could, but I like to annoy people with having it unsolved on the shelf. It also takes me quite a long time. Okay, so when WanaCrypt installs itself and it starts running, it needs to generate some keys, but it's going to use to encrypt your files. The first thing it does is generate a public and private key pair for this infection. And these are for the client, right? So let's call them C pub and C private. So we've generated a public key and a private key, right? Now these are 2048-bit RSA keys. Skipping over the math a little bit, to try and calculate the private key, if we didn't have it, we would have to solve a very large integer factorization problem, which is not happening, right? Suffice to say. So normally what a ransomware would do now is whip this private key off to a command and control server, delete it so that we never get it back unless we pay a ransom, and then encrypt everything with this public key, right? But in a hybrid encryption scheme, it works slightly differently. Stored inside the executable is a server's public key. This is a command and control server. So this that we have here, an S pub. Now, this public key has an associated private key, but we have no idea what it is, right? It's stored somewhere on one of those command and control servers, or all of those command and control servers, and these were generated when the ransomware was created, right, a while ago. So the client's public and private keys are generated on the fly for every time it installs itself on anyone's machine. The server's public key is stored inside the executable and is always the same, right? And it's associated with the server's private key hidden somewhere else that we haven't got access to, if only we did. It's worth mentioning at this point that if we could find the server and get this private key, that would be good news, right? We could decrypt everyone's ransomed files, perfect. It's hidden on the dark web, right? So the onion addresses that are supplied, hard-coded into WanaCrypt, point to servers somewhere on the planet, but we don't really know where, right? We will deal with hidden services on another video, because I think it's a really interesting topic. What the client then does, what WanaCrypt does, is it's got to try and protect this private key so that it can hold it to ransom. So what it does is it encrypts it with the server's public key. So let's say it takes these down here and it produces spub of C private. Right, this is my strange notation that I'm sort of making up. This is kind of right, but so this is encryption, right? And we've encrypted this private key with the public key, right? So now it's totally useless. It's completely mangled. We can't use it. Remember that in RSA, these perform the opposite task. So for example, if I had all my files encrypted with cpub, I could decrypt them all again with cprivate, right? So that needs to, so the malware needs to stop me from getting to that file, which it's done now by encrypting it. We can't decrypt it again because we don't have the server's private key. That's the issue here, right? So then what happens is, for all files, the client will generate a AES key, which we'll call KF for file, right? And encrypt the file with KF. Then, so we're going to store, in essence, cpub of KF and KF. Okay, so let's look at what I've just written here. Each client has its own public and private key pair, right? Now that's important because theoretically, if one person paid the ransom and they sent them, let's say, the shared private and public key pair, then everyone, you just need to pay the ransom once, problem's gone away, right? That's not a foolproof solution. So what we do, we generate a KF AES key for every single file. Then we encrypt the file with that. So let's just draw that in so it makes it sense. KF file, right? So we encrypt the file with KF. Then we store that file on disk. And we attach to it that key so that it can be undone, but we hold it to ransom by encrypting it with our client's public key.
So let me run this through. Files are all encrypted with a symmetric key, so they're encrypted quickly.
Yeah.
But then that symmetric key is then encrypted with a brand new generated asymmetric key pair,
Yeah.
which is encrypted with the server's public key so that only the server can decrypt it.
Exactly, right? So there's a kind of chain of decryption here that we would have to solve if we wanted to undo all this and get our files back. We'll pretend there's just one file on the disk. To get our file back, we need to decrypt it with KF, right, which is a symmetric key. Unfortunately, KF has been encrypted with this public key here for the client. So we need to work out what the private key for the client is. Unfortunately, again, the private key has been encrypted with the public key of the server. So the only way we can find this private key is to ask the server for its private key, or more likely, ask the server to decrypt it for us and send it back. So you can imagine a situation where you paid your ransom, right? Someone on the other end decided that was okay, and you're going to get your files back. So to be clear, you shouldn't pay the ransom because it encourages crime, and there's no guarantee they'll do this. And in fact, with WanaCrypt, it looks like they're not really bothering, right? Partly because there's a few implementation issues. It's not clear whose bitcoins you're paying to. You should have had so most ransomware will have a bitcoin assigned for your client. So when it generates these keys, it will also generate a bitcoin address, right? So theoretically, this is all automated. You would pay the ransom, and then theoretically, they would choose to, they look at that bitcoin address and go, okay, yes, someone's paid, we'll send them back their private key. Not the case here, right? It seems to be kind of manual, and I'm not convinced anyone's actually doing it. But I can sympathize with people who have had their files encrypted, right? It's one thing to say, don't do it, but you can imagine it if you're in a situation where your family photos have been encrypted, you might be quite desperate to get them back. So, hypothetically, if someone paid a ransom and it was going to give it back, what would happen is the client would send off this encrypted private key, right, which it doesn't know anymore, to the server. And the server would decide, okay, they're allowed their files back for whatever reason, and would decrypt this with their private key. So spriv, right, which I'll put in here, sprivate, SPRV, right? So they decrypt our client's private key with their server private key and send it back over the network, right? This is all happening over Tor, by the way, nothing going over the open network. We then have this private key back again, which we can use to decrypt our KF, which we can use to decrypt our file. And then it just iterates through all the files doing that process. So you can see that the thing they're actually holding to ransom is the fact that we don't know this private key, and they've encrypted our private key. The benefit of this approach is you get the speed of AES, which over a bunch of files on a disk is unbelievably quick. Somewhere around, I think, 700 megabits per second of encryption rate, I think, on a decent Intel machine with AES instructions on it. You get that benefit, but you also have the benefit that the private key, the master key, as it were, is held only on the server and never needs to be sent to anyone. And the only way to undo all of this encryption is to know what that is. And the other bonus is that you don't have to be online to do any of this. Some ransomware, if it can't connect to the command and control server, will immediately shut down, which is nice of them, I suppose, because it means they're not going to encrypt your files if they know you can't get them back. But this doesn't do anything like that. This encrypts your files first, asks questions of the server later. So if the command and control servers disappear, there is no hope because this private key is gone. That's the idea.
Surely at some point this AES key is in the clear because it's got to be generated.
Yeah, and so is this private key, right? So at some point, while it's running, this private key will exist, and before it's encrypted, it will be in memory. Now, there's a few problems with this. First of all, it's way too late for most people, right? But theoretically, if an antivirus was being vigilant, that might help, but not really. The other thing is that it's quite hard to access memory for other processes because of fairly good security measures in Windows and Linux and any other operating system that separate out processes from one another. So really, this is operating in its own address space. It's quite hard for anything else to sort of get in there and quickly look at the keys and stick them in a file in that time period. So really, that isn't, I don't think, an avenue of research in terms of trying to fix this problem. Much better to do things like the web-based sinkhole that stopped it running completely, and then keep a vigilant eye out for new variants that show up, daily now.
Is there any way of working out how it's generating those keys and using that technique to...
If it was using a poor encryption library, right, then maybe there would be a weakness that you could use. Right? As it is, to generate these keys, it's using a Windows standard encryption library, which is not poor. It's perfectly good. So that's going to be a problem. The best bet at this stage of getting your files back is not paying a ransom. It's hoping that someone will find this server, the real location of it, and extract this master key. At that point, everyone else, a tool will be released within a day, but just does all this reverse process and solve the whole problem. This has happened in the past to ransomware that's been brought down. I believe CryptoLocker, for example, was an early ransomware, but when they finally brought down the server, they also extracted the master key and were able to publish tools to undo everything. There's no guarantee that will happen in this case, right? The dark web makes it quite hard to find these servers, especially if, for example, the massive publicity surrounding this has caused them to essentially just do a runner. Maybe not even, I mean, I think the servers are still running, but I don't know. But what the end game for this is, we don't know. Will they find the servers? Won't they? Will this just all sort of disappear? And unfortunately, some people have lost some files. We'll have to wait and see.
Start doing backups now.
Yes.
What's the best way to do backups then?
Okay, hang on. You put me on the spot now.
Yeah,
so the best way to do backups is multi-location, right? So not a single hard disk, because it might die, but also not two hard disks sitting next to each other in case your house falls down and smashes a hard disk. Cloud storage is very good because they have this multi-site redundancy built in, if you don't mind giving your files to them and paying their costs, right? So I use some combination of cloud storage and hard disks and burning to Blu-ray and things like this.